All right, so chapter 5, we're going to start using a lot of our trig. Lucky for you, we don't have to graph it anymore. Lucky for you.
I just don't even like the whole photo.
Well, see this whole front page that I gave you? Are there any problems on this front page? No. So, you are to memorize.
Even better.
Now, I have to tell you, when I took pre-calculus, well, in high school I didn't have to memorize it, but in college I had to memorize it, and you're taking a college level course actually, out of a college level book. You're memorizing it. I fought it tooth and nail, and I got really mad about it. I'm like, really? I could just look this up. I really don't need to. But because I'm sending you off to college, most of you next year, you need to memorize it because your universities expect you to know them. If you're going to calculus, your calculus teacher expects you to know them. In fact, my conversation with said calculus teacher yesterday said, you don't know them. I'm like, because they don't memorize them. So you need to memorize this whole page. Now before you stress, let's look at it. Aren't these already familiar and known? Right? You knew these from the last chapter, correct? Didn't you learn these in the last chapter? Okay, so you know reciprocal identities. You know the quotient identities, which is tangent and cotangent. So you already know those. Shouldn't have to memorize them. Then and according to Mrs. Nelson, you know these, and it should not have been new to you from Algebra 3-4. Well, that's what she said. That's what she said.
I didn't cover it.
And neither here nor there, you had this last chapter, right? So you know the Pythagorean identities. What is new to you are these two sections, and watch how easy they are. These are called your cofunctions. Don't you associate sine and cosine kind of together? Didn't you learn them together? And aren't the middle of all of these pi over 2 minus u is going to represent some number? Like it might be pi over 2 minus 30, like a degree. And so they're all the same on the inside, aren't they? What's pi over 2? What degree measure? 90 degrees. So it's all taking 90 degrees and subtracting some number from it. So aren't they all in the first quadrant? Okay. So if we take the sine of, oh, and by the way, if I'm taking 90 degrees and subtracting an angle measure from it, aren't they what? Supplementary or complementary? Complementary. Aren't they all in the first quadrant then? Right? All right. So if I take the sine of this angle here, it's going to be the cosine of just u. So let's say that this angle measure here, because it's going to be something less than 90, is 40. What was u? 50, right? So the sine of 40, this whole thing, will be the cosine of 50. Do you see what I'm saying? So doesn't tangent go with cotangent? Doesn't secant and well, what's left? Secant and cosecant, right? So wouldn't they go together? So essentially my point to is this, and then they reverse. If you're taking the sine of 90 minus some number, it's the same as the cosine of that number that you're subtracting. That's, if I were you, how I would learn it. Okay? So you have to learn that. And then the other one that is new, didn't I go over even odd identities? Didn't we talk about this? I'm pretty sure that was in the last chapter.
But then we never did anything.
We did a few problems with it. I didn't test you over it. You're going to get tested over it now. So watch this again. The only ones that are different from the other, there's 4 that are alike and 2 that are different. Aren't these 2 different than the other 4? If I take the sine of a negative angle measure, isn't it equal to the sine of that positive angle measure, but times a negative? In other words, the answer to this is going to be a negative.
Wait, how are these two different?
Well, I'm going to get to that. Hang on. So what's the sine of 30 degrees? Caitlin hasn't memorized. What's the sine of 30 degrees? Take out your handy dandy
Wait, isn't it one?
circle. Here's 30 degrees, 1/2. I'm shocked you didn't have that memorized. All right, so the sine, wait a minute. So the sine of negative 30 degrees, won't it be negative 1/2? If the sine of regular 30 degrees is 1/2, then what's negative 1 times 1/2? Negative 1/2. My point is, find the sine of the positive angle and just multiply it by negative. Isn't that all they're asking you to do? The cosecant, find the cosecant of the positive angle, multiply it by -1. In other words, change its sign, right? So, and these four are all the same. What about these ones in the middle? If I'm trying to find the secant of -30, it's just the secant of 30. The sign does not change. The secant of -30 is exactly the same as the secant of 30. The negatives and the positives have the same answer. You don't change it. These ones, you change the sign of the positive degree. And we'll work with some of those in a minute. All right, so those you have to memorize. So there's not really a whole lot new, but you're going to have a property quiz next week over this. You have to regurgitate it. I'll give you a practice sheet on it so you can practice it, so you can copy it as many times as you want to at home and practice it as many times as you want to at home. Okay? You'll be fine. I actually am giving you this quiz, no matter what you do to me in class. All right, so flip it to the back. These are your 4 problems for today.
I like that word.
So we're going to have to flip back and forth to the front page a little bit. We're going to verify a trig identity. It's very similar to what we did with your trig proofs. Remember those ones that you had fun with? That we used these a lot on? Right? Remember those? Well, let's look at number 1. All right, so we have the sine of theta over 1 plus the cosine of theta plus the cosine of theta over the sine of theta equals cosecant of theta. What do you think I'm trying to do?
You said a lot of words.
What do you think my end goal is?
Something equal to.
I want to get the left side equal to the right side. What do I want the left side and the right side to look like? If this is what I start with. Which side looks simpler? I want to change this side to look like that side. So when it says to verify an identity, it means to verify that this side is equal to that side. So I need to verify that this will turn out to equal the cosecant of theta. How do we do that? All right, this one's a little harder, I'll grant you that. If I were to add these together, can I, the way they are? No. I have to have a like denominator, don't I? What is the least common denominator for those two fractions?
1 plus cosine theta sine times sine.
This is fully factored, isn't it? 1 plus cosine of theta, and then this is fully factored because it's only one term. So you're right. It is sine of theta times 1 plus the cosine of theta. Since they're both fully factored, I would consider them prime. So you're going to multiply them together. What is the first fraction missing from the LCD so that this looks like this? Sine of theta. So I have to multiply top by sine of theta, the numerator, and the bottom by sine of theta. Then what is the second fraction missing? Right? So I have to multiply this by 1 plus cosine of theta and the top by 1 plus cosine of theta. So when I do that, I end up with sine of theta times sine of theta. Isn't that sine squared theta? Doesn't it look like this? These multiplied together gives me this. Over your LCD of sine of theta, 1 plus cosine of theta. Plus, if I were you, I would go ahead and just multiply this out. So cosine of theta times 1, cosine of theta. Cosine of theta times cosine of theta is plus cosine squared of theta, all over sine of theta, 1 plus cosine of theta, equals cosecant of theta. Now, can I combine them as to one fraction? Can I combine them over the same denominator? Yep. So as I combine the numerator, what do you notice about these two things right here? What does sine squared plus cosine squared equal when I add them together? Yeah, look at the back. That's an identity, right? Can't I replace sine squared plus cosine squared with 1? So I'm going to, as I'm combining, I'm going to replace these two with 1. So I end up with 1 plus the cosine of theta all over sine of theta, in parentheses 1 plus the cosine of theta, equals cosecant of theta. Don't lose your left and right side. I'm going to put the numerator in parentheses. Why? These cancel out because they're factors of each other, right? So this is, the whole thing is one factor of the numerator, this is a factor of the denominator, they can cancel out. That leaves me with 1 over the sine of theta is equal to cosecant of theta. What can I replace 1 over sine of theta with? Guess what that equals? Cosecant of theta. 1 over sine is the same as cosecant of theta, and that equals cosecant of theta, and we have verified the identity. That the left side does equal the right side. You thought you'd never see that again. No yawning. All right, now example 2, we're going to spend quite a bit of our time looking at example 2 because there's 4 parts to it. We're factoring. Yippee skippy. I'm going to go through a lot of the different factoring, kind of remind you of what's going on. You need to identify this with all the different common factor patterns that we've talked about before, right? Your 4 years here at Horizon or wherever it may have been. This is something squared minus 1. Isn't 1 a perfect square? Isn't this a perfect square minus a perfect square? That should relate to a squared minus b squared equals the difference of 2 squares, right? What's the factor pattern for the difference of 2 squares? A plus b, a minus b. So, how did I get a? That's the square root of a squared. How did I get b? That's the square root of b squared. So I know that this factors into 2 binomials with a plus and a minus. What is the square root of secant squared? So secant of theta goes here. And what's the square root of 1? 1. So this factors as secant of theta plus 1, secant of theta minus 1. Uh-huh. I'm gonna sneeze. No, I'm not.
Achoo. What? Wait, is it plus 1 minus 1?
It's plus 1 minus 1. I squeezed it in there, sorry. Then we have this right here. If I were to write x squared or plus x minus 6, would that be more to your liking? What did I let x be? Sine of theta. So now we're going to factor this simple trinomial. And if you recall, there's no coefficient from the squared term. So we take the constant, in this case 6. Because 6 is negative, we're going to subtract our factors of 6. And we're looking for a middle term here of a positive 1. What factors of 6 subtract to give you 1? So 2 and 3 subtract to give you 1. The sign of my middle term 1 is positive. That means my bigger number 3 gets the plus. What does the 2 have to have? A negative. Because there's no coefficient from the 2, I'm done. I can just throw these into parentheses. But instead of x minus 2 and x plus 3, what did I let x be? So I've got sine of theta minus 2 and sine of theta plus 3. That's not so bad, is it? Well, the next one's probably the most difficult one. You see tangent theta there, right? So if I were to replace this with 4x squared plus just an x minus 3, would that look better? Didn't I let x be tangent, or didn't I let tangent of theta be x? All right. This time, though, when we do our t-chart, what am I multiplying together to go here? Yeah, I want to take the 4 and I'm going to multiply it to the 3. So 4 times 3, because there's a coefficient there. These are different because this one has a coefficient, that one didn't. So 4 times 3 is 12. So I'm going to find the factors of 12. Because your constant is negative, again, we're going to subtract. If this constant here were positive, you would add. And I'm looking, huh? Well, it is negative 12. And you can put that there if you want to, but I don't want that to mess up your sign, so to speak. Because it's negative 12, that's why we're subtracting. If it were positive 12, I'd be adding. If you want to look at it that way. Okay? So I'm subtracting 12 to get factors of 12 to get 1. Which factors would that be? 3 and 4 subtract, give you 1. My middle term 1 is positive
Wait, I didn't really
because my middle term is
Oh,
1,
no.
right? This is always your middle term. And so my middle term is positive, so the bigger of the two numbers gets the positive. What does the 3 have to be, a plus or a minus? It has to be a minus for those to combine to give you positive 1. Now, because there's a coefficient there, we cannot just throw them into the parentheses. So we're going to do group and garbage over here. So I'm going to rewrite this here. So I've got 4x squared. These are my two new middle terms. So I have minus 3x, that's where the minus 3 comes from, and then plus 4x, and then minus 3. So I replaced this middle term of positive x with a minus 3x and the plus 4x. With group and garbage, you split this down the middle. What's the GCF in the first grouping? Just an x. Pull that out in front, divide each of these by x. What do you have left? 4x minus 3. So our other parentheses had better have what's left is a 4x minus 3. What are you going to pull out from here? Just a 1, right? They don't have anything in common. So our greatest common factor would be a positive 1, which means we're not really doing anything. Don't we have a 4x minus 3 left over? All right, so then, don't they have a 4x minus 3 in common? So we pull that out in front. And then what's left? X plus 1. So that was the fun one, right? So then, to factor this, we've got 4 times x. So we got 4 times, isn't our x tangent of theta? Minus 3. And then x is tangent of theta plus 1. So you ignore the trig until the very end. Are you done? Yeah. Oops. All right, so then let's look at the last one. This time we have cosecant, and cotangent. Icky. We don't have the same things, right? Yes.
I think the last one, I usually, like you have negative 1 on the top, and now we don't positive 1 on the bottom.
Negative 1 where? I had minus, I was subtracting the factors of 12 to get a positive 1. So I didn't have a minus 1, I had a plus 1. My middle term is positive 1.
And negative positive.
But the negative means I'm subtracting. It's not a sign, it's subtraction. You're either going to have a minus here or a plus here, meaning addition or subtraction.
No.
So Caitlin and I were talking and saying if you wanted to say, well, this is 4 times negative 3, and make that a negative 12, and then knowing that that's a negative 12, then you're subtracting. So if the 12 is negative, you're subtracting the factors. If the 12 is positive, you'd add the factors. You can look at it that way.
Okay.
Does that make sense?
Yeah.
Okay. Anytime I see something squared, my ears just perk up. Why? Why?
It's not funny.
Why? Oh, yeah. Don't I see something squared over here?
Oh.
Oh, cosecant squared. I can do some replacement, right? So cosecant squared, and the reason why I like that is because what does cosecant squared equal here? 1 plus cotangent. What's the other thing I had here? Cotangent. So I'm going to take the 1 plus the cotangent, and I'm going to replace cosecant squared with that. So this becomes 1 plus cotangent squared x minus cotangent of x minus 3. So before I can factor it, just factoring belong to that one, I need to put it in proper order. The squared term has to come first, so the cotangent squared x needs to come first. Then the plane x is minus cotangent of x. Then aren't these right here like terms? The 1 and the negative 3? Don't they combine to give me negative 2? Are you okay with that? So the difference about this one was we replaced cosecant squared with its identity function 1 plus cotangent squared x. And then I combined like terms and wrote it in proper order. I'm going to get rid of the trig and just look at x's. So doesn't this become just x squared minus x minus 2? Right? So let's do our t-chart.
Wait, isn't the x squared x? Or x squared tangent?
I'm replacing cotangent of x with just an x. Okay?
Okay.
I know the x's are confusing, so if you want to use y's, you can use y's. So I'm going to use Mike and Caitlin's version of the t-chart, just so you can see how it might look. So if I multiply the coefficient here, 1 times negative 2, we would get a negative 2, right? Does that mean I'm adding or subtracting? So I'd be subtracting the factors of 2, and I'm looking for a middle term of negative 1. There's only one set of factors for 2, isn't there? 1 and 2, do they subtract to give me 1? Yep. And so the value of that middle term is negative 1. So that means the 2, the bigger of the 2, carries that sign. What does the 1 sign have to be? Positive. Since there is no coefficient in front of the front, I can just throw these into the parentheses here, right? So I can have a plus 1 and a minus 2, but we're not using x. What are we using? Cotangent. So we have cotangent of x plus 1 and cotangent of x minus 2. Wasn't that fun? Do you see why factoring will never, ever, 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 ever go away? You were hoping in Algebra 1, 2, oh, I'm never going to use this again, so I'm going to ignore it. You're still going to use it in calculus. It does never go away. It's a basic foundation. All right, so example 3. You're going to rewrite the expression of 1 over 1 plus sine of x so it is not in fraction form. So the minute they say that, you see the denominator here? We are going to multiply by its conjugate. We use that word conjugate in Algebra 2, Algebra 3, 4, geometry. What do you think the conjugate to 1 plus sine of x is?
1 minus.
Very good, 1 minus sine of x. So I'm going to take 1 over 1 plus sine of x, and we are going to multiply numerator and denominator by 1 minus sine of x. Isn't that a form of 1? I'm not changing its value, I'm giving it a facelift and making it look different. And the reason to my madness is this. Isn't this the difference of t-squares factor pattern here? 1 plus sine of x, 1 minus sine of x. Okay? So I'm going to put parentheses around this and this. This ends up giving me 1 times this is 1 minus the sine of x. So that's your numerator, right? If I use a squared minus b squared, this is a and this is b. If you want to FOIL this out, that's fine, but look what happens. 1 times 1 is 1. What's 1 times negative sine of x? Negative sine of x. What's sine of x times 1? Positive sine of x. Don't they cancel each other out? Okay. What's a positive sine of x times a negative sine of x? Negative sine squared of x. Isn't that a squared minus b squared? So you can skip that. And you're like, well, what was the point of that? I see something squared. Why is that important? If you look on the other side, oh, there's sine squared. Now, that's not quite the way I have mine. So sine squared plus cosine squared is equal to 1. What do I have here? 1 minus sine squared x. So if I were to make this into 1 minus sine squared x, wouldn't that mean I'd subtract the sine squared x from both sides? What would 1 minus sine squared x equal? Cosine squared x. So can't I replace this whole thing right there with cosine squared of x? 1 minus sine of x over cosine squared of x. You're like, oh, it's still a fraction. Yes?
I don't understand how you was missing.
You'll see. Because I can. And you'll see my madness in the end. As you get used to this, you're trying to get it into one of those identity forms so you can exchange it for something else. And then hopefully you're writing good notes, and you're going to write yourself the following note. At this point, you're going to split into two fractions. And I'm running out of room, so I'm going to start working to the side. So if I split it into two fractions, 1 over the cosine square root of x minus sine of x over cosine square root of x. I'm slowly getting there. What's 1 over cosine square root of x? What can I replace 1 over cosine square root of x with? Look on the other side. What's 1 over cosine of x equal to? 1 over cosine of x. Where'd it go? Here. It's equal to secant, right? So what do you think 1 over cosine squared of x is? Secant squared of x. So I can replace this, whoops, right here. So this is something new that you've learned with those. I can replace that with secant squared of x. Is that a fraction anymore? Is it? Nope. Minus, I'm going to change this up just a bit. Wouldn't you agree that this is equal to sine of x over cosine of x times 1 over cosine of x? I'm a great manipulator. Why would I do that? What do you know that is? Tangent. What's this? Secant. So then my final answer without fractions would be secant squared of x. We just did that one. Minus, these are multiplied together. This is tangent of x times secant of x. Do I have any fractions anymore? Good howdy, right? There's my final answer. That was a tough one. I'll grant you that. But you're trying to manipulate things. You're trying to get things into a form that you can substitute it with. So I like to get things into sine and cosines because those are easier to substitute in, or anything that's squared are easier to substitute in. I couldn't do anything with, where was it? This right here, because I don't want to go back and replace this with what I replaced it with originally. I don't want to replace it with this because I can't do anything with that. So the more of these that you practice, the better you get at them. That's all I can say. Make sure you do your homework and check it. Yes.
I'm still confused as to why you could use 1 minus sine squared of x with cosine squared of x anyway.
Because it's much more difficult to work with.
No, I mean, what, I looked at the back of the paper and I don't see anywhere where it says 1 plus sine squared of x equals cosine squared of x.
Right here. See this right here? See that one right there? I can manipulate any of these however I want to. Because I had because I had 1 minus sine squared of x that I was trying to replace, I wanted to make this into 1 minus sine of x. So I just subtracted. So you would agree that cosine squared of u is equal to 1 minus sine squared of u. So because I had that, this is another equivalency. They're not going to give you all the different forms of these that you could have, but you can move them around as much as you want to. And so you're like, okay, I have sine squared in there. How can I make this look like what mine is? And so that's what we did. Good question. Does that make sense now?
Yeah.
Okay. Anything else about this as to why I did what I did? You're like, well, I would not have thought to do it that way, right?
I just want to.
That's why I've done one with you, at least one. Well, we've done a couple now. And then you're going to do more in your homework, right, Kayla?
Yeah.
How can she fall asleep during this exciting discussion? And my point is that you really have to do your homework because that's where the experience comes into play. And there's not going to really be an answer on this homework. It's going to say answers are varied. I know. So you're going to have to, I can show you my work tomorrow. And you can see, and if your work is different than mine, you can ask me, could I have done it this way? And we'll look at it and see, could you have done it that way? Okay?
So then, like, on the test, it's gonna be like
We're going to spend a couple of days on this, by the way.
have like several different ways to do it.
Yeah, and I have to follow your way, and it has to be logical. If I can't, it's better to show more work than less, because if I can't follow what you did, I'm not going to accept that step. Does that make sense? So showing more work is better than showing less. You might want to write that in your notes. More is better. Usually it's less is better, but here more is better. Okay? Last problem. Again, this whole thing has been all about manipulation and substitution, right?
Yeah.
What can I substitute for what? And we try to substitute out the trig with just a plain x in order to make things easier, but this one happens to be just the opposite. We are going to use the substitution. We're going to say that x is 2 times the tangent of theta. So this time we're replacing x with the trig. Okay? So it's kind of backwards of what we did above here. To express the square root of 4 plus x squared as a trig function of theta. So all you're going to do is take this 4 plus, and instead of x, isn't it x squared? Aren't we letting x right here be 2 tan of theta? Don't worry that theta is in between 0 and pi over 2. In other words, theta is in the first quadrant. It's between 0 and 90 degrees. Don't let that bother you. It's not a huge important factor yet. All right, so then we're going to go ahead and move forth. If I were to square this, there's no addition or subtraction here, right? It should be an easy squaring. The 4 stays the same, plus 2 squared is what? 4, and tangent squared is tangent squared theta. I see a tangent squared in there. What's there that I don't want? Zach?
Since you're trying to take the square root, can you just take the square root of both of them?
No, you can't take the square root of this and square root of that, because there's a plus here. But here's what I can do, and we're going to get to that in a minute. Don't we have a tangent squared here? From the back, I have a tangent squared here. What is not here that's underneath the radical? I'm going to want to, okay, so I've got 1 plus tangent squared. I'm probably going to want to replace what's underneath that radical with a secant squared, because I can take the square root of that, right? But I don't have 1 plus tangent squared here. What do I have? 4 plus 4 tangent squared. Don't they have a common factor of 4? We're going to factor out of 4 using division, right? So I'm going to rewrite this as 4 times, divide this by 4, don't you get 1? Divide this whole thing by 4, don't you get plus tangent squared theta? Now, isn't this exactly what's on the reverse side? It's all about manipulation. See, you guys are supposed to be experts at manipulation. You're teenagers. Oh, with your parents, but not with your mathematics. All right, so 4, I'm going to replace 1 plus tangent squared theta with what? Secant squared theta. Now, Zach, can't I take the square root of those that are under there because I no longer have an addition or subtraction sign, right? And so the square root of 4 is 2, and the square root of secant squared is secant of theta. Ha! Done.
Yeah.
Wasn't that exciting? So I'm going to separate these.
Thank you so much.
Don't you love pre-calculus?
Yeah. It really makes sense.